In this video, we will learn how to evaluate different types of improper integrals. From the fundamental theorem of calculus, we learned that if a function f of x is continuous on the interval ab, then we can integrate the function and it becomes f of b minus f of a, where this capital F is the antiderivative of small f. Therefore, we had two conditions in the fundamental theorem of calculus. The first condition is the limit ab has to be finite, and the second condition is the function f of x has to be continuous on the domain ab. Now, if an integral fails to satisfy any of these two conditions, then that would be an improper integral. If an integral fails to satisfy the first condition, that is, if the lower limit a approaches negative infinity or the upper limit b approaches positive infinity, then that would be infinite integrals. Sometimes it also called improper integrals of type 1. For example, here the upper limit b approaches positive infinity. In this example, the lower limit a approaches negative infinity, and for this one, both lower and upper limit approaches infinity. One is negative infinity, another one is positive infinity. Also, if an integral fails to satisfy the second condition, that is, if f is not continuous on the bounded domain ab, then it is called discontinuous integrals. Sometimes it also called improper integrals of type 2. For example, this function is discontinuous at the upper limit x equals to 1. This function is discontinuous at the lower limit a equals to 2. And this function is discontinuous at x equals to 1, which is between the limit 0 to 3. Methods to evaluate improper integrals. If the function f is continuous on this interval and the upper limit is infinity, then replace this upper limit by b and write limit of b approaches infinity. If the lower limit is negative infinity, then replace this lower limit by a and write a approaches negative infinity. Now, if both lower and upper limit approaches infinity but in opposite sign, then divide this interval into two subintervals. One from negative infinity to c, negative infinity to c, and another one is c to positive infinity, where c is an arbitrary constant in this interval. Now, to evaluate this part, follow this technique, and to evaluate that part, follow this technique. So, in this example, the upper limit is infinity, so we replace this upper limit by b and write b approaches infinity. After integrating, we got this line, and when b approaches infinity, this term approaches 0. And after simplifying, we got 1. Since 1 is a finite value, so this one converges. In this example, the lower limit is negative infinity, so we replace this lower limit by a and write limit of a approaches negative infinity. After integrating, we got this line. Now, when a approaches negative infinity, this term approaches positive infinity. And it doesn't matter if we add any number with positive infinity, it will be positive infinity. Since positive infinity is not an finite number, so this one diverges. In this example, both lower and upper limit approaches infinity but in opposite sign. So we divide this interval into two subintervals. One is from negative infinity to 0 and another one is from 0 to infinity. Now if we integrate this one, then we got negative 1/2, and if we integrate this one, then we got positive 1/2. To get the complete result, we need to add them together, and after adding we got the result as 0. Graphically, from 0 to infinity, the graph is above the x-axis and the area is positive, and from negative infinity to 0, the graph is below the x-axis and we got the area as negative 1/2. After adding the same amount of positive and negative quantity, we got 0. Methods to evaluate improper integral of type 2. If the function f is continuous on the interval ab and has a discontinuity at a, then we replace this lower limit by c and write c approaches a plus. This a plus means we are taking any value of a which is more than a. If the function f is continuous on ab and has a discontinuity at b, then we replace this upper limit b by c and write limit of c approaches b minus. This b minus means we are taking any value of b which is less than b. If the function f is continuous on ab except at c in ab, then we divide this interval into two subintervals. One is from a to c and another one is from c to b. Now to evaluate this part, follow this technique, and to evaluate that part, follow that technique. For example, here the function 1/x cube is discontinuous at x equal to 0, so we replace this 0 by c and write limit of c approaches 0 plus. That is, we are taking any value of c which is more than 0. Now if we integrate, then we got this line, and when c approaches 0 plus or 0, then this become infinity and the final result is infinity, and this integral diverges. In this example, the function is discontinuous at x equals to 1, so we replace this 1 by c and write limit of c approaches 1 minus. That is, we are taking any value of c which is less than 1. So if we integrate, then we will get this line, and when c approaches 1, then it becomes infinity. That means this one diverges. For this example, the function 1/x square is discontinuous at x equal to 0. So we divide this interval negative 2 to 5 into two subintervals. One is from negative 2 to 0 and another one is from 0 to 5. Now if we evaluate this part, then we see that it diverges. Since one part diverges, then the original integral also diverges, and we do not need to evaluate the other part. Thanks for watching.